I met our next speaker. I'm trying to think of the year. It was a long, I don't know what year it is, so let's go with that. Let's go with that roughly. I was lost in Cambridge trying to find, well, no, that's actually true. I had a dinner in Cambridge, and I had about 40 minutes till dinner, so I wanted to check out MIT's campus. So I saw two guys walking along. I said, hey, can you point me to the campus? And he says to me, well, I have a final tomorrow, so why don't I give you a tour? Right? He was trying to avoid studying, apparently. And it seems to have worked out well for him, because somehow in his studies, he also learned Japanese, which has nothing to do with that. Everyone, please welcome Ben.
Hi. I'm Ben. I am one of the founders and the CEO of Espresso AI. Excited to be back here. I think the last time I talked here was like 10 years ago. I think so. Had a lot more hair. It was a different startup. We're going to talk about AI with ROI, using ML to cut your Snowflake bill in half. AI with ROI means we actually save you a ton of money. Most people in the audience probably know this. Actually, who's used a data warehouse before? OK. Who uses Snowflake now? You should all come up to me after the talk. We should chat. For people who aren't familiar with it, a data warehouse is basically a large cloud database that's optimized for analytical queries. So not transactional queries that need to go really fast, but long queries that take a variable and often large amount of compute. The idea is that you are separating the storage from the compute, relying on the cloud to scale it out for you. Roughly speaking, you can think of it as sticking all your data in S3 and then auto-scaling EC2 on demand to do the compute. We optimize how Snowflake and Databricks now, Databricks SQL, process queries, saving our customers millions of dollars in the process. You can set it up in a few minutes, instantly save 80% on your bill. Here's the bill before. Here's the bill after. That's pretty much the entire user experience, so now I get to just geek out for the rest of the talk. Before this, I worked at Google for 7 years doing performance engineering and machine learning, and this is machine learning for performance engineering. So we structure this entire problem as constrained optimization. How do we run all of your workloads as cheaply as possible without increasing the latency of any of your jobs? Right? The idea is you turn it on, everything is cheaper and faster, and you don't need to worry about it. We do two things. We're going to jump into both. One is scheduling. The other one is query optimization. What is scheduling? Scheduling is the computer science idea of how do you allocate workloads across different machines in your cluster. If you're familiar with Kubernetes here in the real world or Borg at Google, it's the same idea. You have some existing fleet of machines, you have some jobs coming in, and you want to know where to put each job to satisfy the requirements of the job and just to not spend a lot of money. This doesn't sound very exciting necessarily, but it's extremely impactful. You can see literally savings of 3, 4, 5x by scheduling things correctly. Snowflake and other data warehouses do scheduling statically. So you often have one cluster that runs all your Tableau jobs, one cluster that runs all your dbt jobs, one cluster for Bob and accounting, and so on. This is really bad for efficiency because you spin up a bunch of clusters that you don't need. And overall, most of the companies that we talk to, they have utilization around 40, 50%. So you're literally spending half your bill on machines doing nothing. If Google ran its data centers this way, they would go bankrupt. You can do better by predicting query runtime and how queries scale. So this is a lot like how Borg and Kubernetes work, but we use machine learning to understand, can this query run on this cluster? How much of a benefit do I get by scaling this query up to more compute, and so on. That way you don't have to hand annotate the queries, which you can't do anyway. There's a paper reference here for how Borg works if you're curious. You need to basically estimate 3 things here. How many resources does each job need? How many resources do I have available on these machines? And then how do you actually do that matching efficiently? We are a company with AI in the name, so we just use ML for every single thing. There's no other alternative, really. With Kubernetes, every job will get hand annotated with how much CPU you need, how much RAM, how much disk, how much I/O, that sort of thing. Snowflake, if you've written a Snowflake query, is just SQL, so there's no annotation there. We've trained LLMs to be able to read a SQL query, to understand your database and your schemas, how much data you have, and predict, okay, this is going to run in this amount of time on this hardware. Same thing for available resources. If you're running your own fleet with Kubernetes, your machines will have some amount of resources, right? They'll have a given number of CPUs and RAM and bandwidth. Maybe they have GPUs. Snowflake clusters don't advertise what they can do. So again, we're just interpolating here, can this run on this machine? And finally, scheduling. So this is a really active area of research, even without machine learning. Greedy bin packing is a good place to start. If you're coming from not doing any scheduling at all, you can do much, much better. Better algorithms will take into account things like job timing, resource spikes, figuring out what workloads are coming, being able to auto-scale, that sort of thing. We do this with machine learning. More specifically, we use reinforcement learning, and we really directly translate that constrained optimization problem into something that a network can learn to do better through RL. So it's literally learning to shuffle your workloads around as efficiently as possible without increasing latency. We didn't have the latency constraint initially, and it just decided to put everything onto one really small cluster and queue all your jobs to infinity, which is the right answer, but not very useful. There's a lot of really cool stuff that you can do here that's really hard to describe in a classical algorithm. A different way to explain this is almost any classical formulation of bin packing is going to be NP hard if you start adding any sort of interesting constraints to it. But for example, you can use you can move some small workloads onto bigger machines that are already running to save money to avoid spinning up new hardware. This is how we get things to run faster. You can learn to understand end-to-end job latency rather than looking at latency query by query. So if you actually understand there's 30 queries coming in from this dashboard refreshing, and I really care about when the last one finishes, not how long each query takes, you can make better decisions. You can queue stuff up to pack things better. BigQuery does a lot of this under the hood, which is why their pricing model is different. Here's what it actually looks like. So this is a very normal setup for Snowflake. You have dbt running on one warehouse, Looker on another, a bunch of ad hoc queries on a third, and altogether this burns 3 credits. Credits are like dollars, but different, and you're more inclined to spend them because there's no dollar sign. You can compress all of this onto one warehouse. Obviously, this is a really simple example, but this is roughly what things look like in production for us. In this case, you save half the money, and really there's no downside at all. Here is a actual example of what things look like, and also you can kind of see why the other example is really simplified. So this is a Sankey diagram from a beta run, And you can sort of see that big red warehouse at the top left ends up being opportunistically broken down across a lot of other warehouses that are running. This doesn't really show the savings, but this saves something like 30 or 40% by just capitalizing on the idle time on those other machines. Cool. The second thing that we do is query optimization. So we do a bunch of query optimization both with and without machine learning. I'm going to primarily talk about the non-machine learning approach for time, but I am ahead of schedule, so I may briefly talk about what we do with ML as well. How many people know what query incrementalization is? Okay. Query incrementalization is a poorly known technique that can save tons and tons on runtime for batch jobs. We've literally seen this save people 90% plus on their workloads. Query incrementalization just means if I'm running an ETL job or an LT job, instead of processing all of the data, I am only going to reprocess the new portion of the data. If you're adding a little bit of data every day, this is basically like an O of n speed up on the amount of work that you're actually doing. This is a really simple example. So if you're just doing select star from a table, that's going to write the same table over and over every day, which is pretty clearly wasteful. Instead, if you have a timestamp that says when the data was actually refreshed and updated, you can change the ETL to just write the new rows. This is really straightforward, so obviously this is a lot better. Why doesn't everyone do this for all of their queries all the time? Well, this is already substantially more complicated than a normal select. It gets much, much worse from here. So if you're dealing with joins, especially multiple joins, if you're dealing with aggregations, filters, subqueries, you need to understand how much there needs to be tracked for every single part of the process, where you need to keep the bookkeeping. Oftentimes, you need to keep metadata somewhere else. And generally, you need to really be able to reproduce the behavior of having written the entire new table. This is not in SQL, but just in relational algebra, writing out how you would efficiently do a join incrementally. The gist is that if you're joining A and B, you would want to write A joined by the new part of B, union with B joined by the new part of A. For everyone who, well, you may notice that this actually looks a lot like a derivative, which is true. This basically is taking the derivative of the entire SQL function. And being able to do that automatically on the fly is really something that compilers are much more suited for than people. The benefit is you don't have to do it the first time, you don't have to read it later. There's a lot of maintainability costs to having incrementalized queries. And you just basically don't need to worry about it. You're not going to make mistakes. You can imagine if you tried to check this in, people may not be super happy with you. Cool. Since I have a few minutes, I'll talk a little bit about the kind of ML that we do as well. So this is a very much a non-ML approach. This is just good old-fashioned compiler work, which is really fun. On the ML side of things, we use LLMs to optimize queries automatically. So the idea for us, and actually the initial idea for the company, was what if we could take a model, train it to take a query as input, and give back a faster query. It turns out that that works. you can train it to work really, really well. One big outstanding question there is correctness. So appropriate to the pile of relational algebra I have on screen, the way that we validate correctness and kind of get everything to work is through formal verification. So entirely separately outside of the ML models, we work with a formal verification library to make sure that the input to the LLM is mathematically equivalent to the output. People often ask if we do something like run the data twice and make sure that the result is the same and then just assume that the output query is correct. We don't do that. That doesn't work reliably. A really obvious example of why that doesn't work is you could have two very, very different SQL queries just return the empty set. That's certainly not enough to say, oh, hey, these queries will always return the same thing for all possible data. The great thing about ML is that you can sort of get the models to do whatever you want if you throw enough compute at it. And so while formal verification might seem like a tough constraint, it turns out that if you actually just train the model to understand what the formal verifier can prove, you can start getting some really good results. Cool. Thank you all for listening. We have a booth out there if you do use Snowflake and you want to chat. You can also shoot me questions. We are hiring if you want to come work on stuff like this.